This is lesson 3.4 on zeros of polynomials. Now in the last section we talked about how to divide two polynomials. We looked at synthetic division and we looked at long division. If you remember back to just division of integers, whenever we would have the situation pop up where if we were dividing two numbers and there was no remainder, so if the divisor wound up giving us no remainder in that quotient, we said that the divisor is a factor of the dividend. So when there's no remainder, we say that we have found a factor. The same is true with polynomials. When we're dividing two polynomials, if there is no remainder, that means that it's a factor of that polynomial. So in other words, we can divide into it with no remainder. We can think of it as something times that factor. Well, for polynomials, we have something a little bit different that's special. Whenever we have a factor, that means we've also found a zero of a polynomial. A zero is going to be wherever an x value where the whole polynomial equals 0. So if x minus c is a factor of the polynomial, that means if I substitute in x equals c, that's going to give me a 0. And if we think about it, this shouldn't be too surprising. If a polynomial, if we can write it as this factor x minus c times something else, well then yes, of course, when we plug in x equals c, that's going to give us 0 times something, so obviously it will give us 0 back. So it's not too surprising when we think about it, but at first glance it's possibly not to be expected. So what we're going to do is we're going to use this fact to help us easily identify whether or not a given linear term is a factor of a more complicated polynomial. Okay, so here's an example of a problem that we might run into. So determine whether x minus 4 is a factor of x cubed minus 2x squared minus 23x plus 60. So from what we said before, x minus 4 is a factor if and only if, so if and only if means if one is true, both of them are true. If and only if x equals 4 is a 0. Now, depending on personal preference, sometimes depending on the problem, you've actually got two different ways you can approach this. The first, and what my opinion is the easier way to approach it, is to just plug in x equals 4 and see if you get a 0 back. So 4 cubed minus 2 times 4 squared minus 23 times 4 plus 60. So 4 cubed, that's 64. 4 squared, that's 16, minus 2, that'll be 32. Oh, 32. Minus 23 times 4, let's see here, that'll be 80 plus 12, so 92. Plus 60, so 34, or rather 64 minus 32, that's going to be 32. Negative 92 plus 60, that'll be negative 32. So aha! So we get a 0 back, so yes, this is a factor of the polynomial. Now, your other option is to just do what we did in the last section. You can actually go ahead and just use synthetic division very quickly to see if this is a factor or not. So we set up our synthetic division and just go through a normal process. Bring down the 1. 4 times 1 is 4. Negative 2 plus 4 is going to be 2. 2 times 4 is 8. Negative 23 plus 8, that's going to be negative 15. Negative 15 times 4 is negative 60. So plus 0, or rather negative 60 minus 60 is going to be 0. So either way you slice it, we conclude that yes, this is a factor of the polynomial. So since all I will be seeing for the drill portion is your final answer, feel free to choose whichever process you like more. Either use synthetic division real quick, or just substitute in x equals 4. Okay, here's another one. So determine whether x plus 2 is a factor of x cubed minus 7x squared plus 8x plus 16. So again, x plus 2 is a factor if and only if x equals negative 2 is a 0. So let's just plug in x equals negative 2 first. So negative 2 cubed minus 7 times negative 2 squared plus 8 times negative 2 plus 16. So negative 2 cubed, that will be negative 8. Negative 2 squared will be positive 4, so minus 28. 8 times negative 2, that will be negative 16, then plus 16. So negative 8 minus 28, that's going to be negative 36. Negative 16 plus 16 is 0, so we get negative 36 here, so no, this is not a factor. Now let me show you something interesting. Last time we saw that when we got a 0 back, when we plugged in our corresponding 0 term to check, we saw that, well, of course, we'd get a 0 back for our remainder. What if we do it for a term that's not a 0? So will we get the same thing back when we have a term that isn't actually a 0, that isn't a factor of this polynomial? Let's take a look real quick and see. So again, you don't need to do both of these for the problem. Pick which one you like to do more. Either plug this in and see if you get 0 back, or use synthetic division and see if you get 0 back. You don't do both. That takes too much time. Do one or the other and make your conclusion based off of that one. But I want to show us both of them just to demonstrate this. So synthetic division real quick, bring down the 1. Negative 2 times 1 is negative 2, so I get negative 9. Negative 9 times negative 2 will be positive 18, so I get 26. Negative 2 times 26, that's going to be, oh, let's see, I think negative 52. 16 minus negative 16 plus negative 52, that's going to be negative 36. Huh. Look at that. The remainder here is the exact same as what we got back when we plugged in x equals negative 2. Is that a coincidence? No. There's not very many. There are coincidences in math, but not too many. This is actually always going to happen. Whenever you plug in a value for x here, you're going to get the same number back as what we would get if you divided by the corresponding factor. So plugging in x equals negative 2, that corresponds to the linear factor x plus 2. So what you get here and what you get here will always be the same. But for the purposes of this problem, our conclusion will be the same either way. No, this is not a factor. So here's something a little bit different. Determine whether x squared plus 4 is a factor of x cubed plus x squared plus 4x plus 4. So now we're looking to see if an irreducible quadratic, notice it's quadratic because the highest power of x is 2, but it's irreducible because we cannot write this as the product of two linear terms. So that's what we mean by irreducible. So since it's quadratic, we can no longer use the synthetic division approach. Remember, synthetic division only works with linear terms. So if you want to do any sort of division here, it's unfortunately going to have to be long division. We really don't want to do that. That's a little bit of a pain. It's perfectly doable, but let me show you a different way you can approach this. What we learned for the drill problems actually still works. This x squared plus 4, this is going to correspond to the x value when x squared plus 4 equals 0. So when does that occur? When x squared equals negative 4. Now if I take the square root of both sides, remember take plus or minus here, square root of a negative number means that we're dealing with imaginary numbers now. So x is going to be plus or minus 2i. We generally don't like working with complex numbers, but actually it's a-okay here. So what we can do to check to see if this is a factor is to plug in x equals either one. You can pick positive 2i or negative 2i. It actually won't make a big difference. But take your pick, plug it into this polynomial. If we get a 0 back, then it's a factor. If we don't, then it's not. So let's try it out. Let's plug in x equals 2i. So I have 2i cubed plus 2i squared plus 4 times 2i. Let's clean that up. That's 2i right there. Plus 4. All right, 2i cubed. When we're working with an imaginary number like this, since we're multiplying these two, we can just treat them separately. So 2 cubed, that's going to be 8. I cubed, if you remember, I to the first power is I squared is minus 1. So I to the first is I squared is minus 1, I cubed is minus I, and I to the fourth is just 1. So I to the fifth, you start over all again. So I cubed in this case is going to be negative I, so I'm going to write this as negative 8I plus, all right, 2 squared is 4. I squared we just said is negative 1, so go ahead and write that as negative 1, plus 4 times 2i, so that's just going to be 8i plus 4. So let's see here, I have a minus 8i here, a minus 8i here. Those cancel out. I have a negative 4 here, or we'll be adding a negative 4. So negative 4, positive 4, those cancel out. So everything's gone. I'm left with 0. So what do we conclude? Since one of these imaginary roots, these imaginary factors is a 0 of this, interesting but true fact is that both of them have to be zeros. Our imaginary zeros, our imaginary roots, those are going to come in pairs. So for example, if I somehow knew that x equals, let's say 3 plus 2i. Suppose I know that this is a 0 of my polynomial. I automatically know that x equals 3 minus 2i is also going to be a 0. These are what we call complex conjugates. If we have one as a 0, they're both zeros. So in this place, or in this case, since I found that x equals 2i is a 0, I also know that x equals negative 2i is a 0. But all we really want to know here is whether or not this is a factor of this polynomial, and it is. Since we found that one of these solutions is 0, both of them are, so yes, this is a factor. So our final answer here is going to be yes. Now, since this would be an application problem, I would want to see some sort of a justification here. I would want you to show me where this complex number came from and show me that yes, we do get 0 back. Or you can go the long way. You can just do long division here and show that we get no remainder back. If for whatever reason you really just cannot stand complex numbers, you can actually get around using complex numbers completely by going that approach. But I'd encourage you, I think this is generally going to be just a little bit quicker and kind of gets more to the heart of what we're talking about here than if we just used long division.